A research team near the coast. Heading north-northwest. "45 kilometers off the sandy beaches of Borkum, one of the most exciting tests in German science is taking place. At the Alpha Ventus wind farm, scientists are finding out if electricity can be economically produced in the middle of the North Sea. How do the wind, weather, and waves impact the nacelles, steel towers, and rotor blades? Can the wind power turbines withstand these forces for 20 years? The RAVE research project is commissioned by the German government to gather experience and knowledge about the future of offshore wind farms. Reliability is one important factor. Repair work out here is laborious and expensive. That's why more than 150 scientists are researching offshore technology in 25 separate projects during both the construction and operational phase. Their results could provide a breakthrough for technology that fundamentally changes the way Germany is supplied with electricity. Spring 2008. Even before construction of the offshore farm begins, engineers are testing a model of the tripod foundation in the large wave flume at Hanover University. The real thing will have to support a wind turbine weighing more than 500 tons on a sandy seabed for many years to come. To prevent the turbines from obstructing views from the beaches of Borkum, or from spoiling the landscape of the Wattenmeer National Park, they have to be located far out to sea. And that's where the waves are especially high. A wave machine simulates the energy. The waves are especially strong when they break on the tripod. The scientists measure the water's force with special sensors. They use the measurement data to optimize mathematical models that provide information about the forces bearing down on offshore parks.
We've determined, through measurements in the flumes, that breaking waves create 17 times more force than waves of similar height that do not break.
That means several times a year, waves crash against the steel foundation with a force of more than 500 tons. The researchers attach an underwater camera to the floor of the wave flume. Over a long time period, the camera observes changes to the sand floor surrounding the tripod. The results are clear. Before long, part of the foundation is exposed. Researchers compare the observations to the mathematical models in order to determine what happens on the real seabed.
The experimental data demonstrates that scours develop relatively quickly. That means the seabed is washed out around the foundational structures. Together with scours formed by tidal currents, we now have very significant forces acting upon the entire structure.
Summer 2008 in Norway. This is where the real tripods that will support the wind turbines are assembled. A colossus made of steel. Each one weighs more than 700 tons. Specially trained welders fuse the steel cylinders to the foundation. The walls are several centimeters thick. The problem is, while the giant tripods have to withstand the enormous forces out at sea, they can't be too big. Every millimeter of steel cladding raises the cost by thousands of euros, making offshore electricity less economical. That's why two engineers from the Fraunhofer IWES are taking a close-up look at the interior life of the foundations. Their goal is to define a structure with just the right dimensions. The scientists attach a special sensor to the wall of the tripod. If the steel body stretches by just a few thousandths of a millimeter per meter, that changes the electric resistance of the so-called strain gauge. This way, the engineers can precisely measure the mechanical changes of the steel colossus in response to wide temperature fluctuations, strong pounding of the waves, and extreme wind speeds.
A test turbine is provided with hundreds of sensors, including additional accelerator sensors, to monitor the entire structure over a period of several years.
Strain gauges, accelerator sensors, and temperature probes. The tripod is not only a foundation, but also an important measuring device. It's part of a mechanical monitoring program to help engineers design an optimal tripod structure. In April 2009, it goes out to sea. In addition to sensors, the feet of the tripod are provided with a special ring structure. Before it goes into operation, engineers have to anchor the 700-ton colossus 30 meters deep into the seabed. And they have to find the exact position, down to the centimeter. They made it. Afterwards, they anchor the steel foundation to the seabed with 3 piles measuring more than 30 meters in length. Before the piles are driven into the seafloor, pressurized air flows into the rings, and a veil of bubbles rises toward the surface of the water. The bubbles are intended to dampen the noise made by this hammer. It pounds the piles with a force of 50 tons once every second for 10 hours. The veil of bubbles absorbs the sound waves. The surrounding area is much quieter. And that's important. The region where the work is taking place is home to porpoises. The sea mammals are sensitive to loud noises and shouldn't be disturbed by the construction clatter. Testing the effectiveness of ecological protection measures like this one is part of the RAVE research program. During the construction phase and later during operation, biologists observe the behavior of other forms of life, for example, migratory birds. How do such animals react to the new wind farm? Are collisions unavoidable? Even before the next foundations are laid in the sea, researchers are investigating the seabed. The entire community of organisms that live on the seabed is known as the ventus. The area must be free of rare species such as the black clam, the mud shrimp, or the edible sea urchin in order for the next tripod to enter the water. The man-made structure could create a new living space for undersea organisms.
The towers of wind power plants attract various kinds of mussels, along with oysters and a variety of anemones. They form an additional source of nutrition for the fish stock found in these areas.
Besides the additional nutrition, the area within offshore parks is generally off-limits to commercial fishing. Ecologists believe that could even lead to a recovery of fish stocks. But vigorous organic growth can also lead to problems. 2 years before the construction of Alpha Ventus began, researchers attached metal plates to a lighthouse just a few centimeters above the water line. The sea plants quickly made themselves at home. The problem is the plants ate through the protective layer. It was designed to protect the sensors from salt water. Offshore farms need constant monitoring in order to ensure trouble-free operation. And that involves the use of sensitive monitoring devices for the minimum 20-year lifespan of offshore wind turbines.
The sample we retrieved from the test station clearly shows that the adhesive layer, as well as the layer of protective coating, withstood more than 2 years of exposure. But we can't say if that would be the case for all 20 years of a wind turbine's lifespan.
But that information is essential for determining if offshore turbines can later be monitored from land when they're located many kilometers out to sea. And it's an important economic consideration as well. That's why a variety of protective coatings are constantly being tested in the laboratory. Instead of waiting 20 years to find out if a coating endures the wind and weather, researchers subject materials to a kind of fast motion process in a special climate chamber. The chamber allows both the mechanical and climatic forces at work on the high seas to be simulated at the same time. Two spray nozzles provide the salty sea air. Even waves crash regularly against the probes. And it all takes place at temperatures ranging from -30 to +100 degrees Celsius. In addition, 2 rollers bend the metal plates with great intensity. It's a force of more than 10 kilograms for 1 square millimeter. That can make a probe look relatively old in no time. But it's not only metal plates and the protective layers of sensors that experience a stress test in fast motion. Fraunhofer scientists also put entire rotor blades through an extreme testing process. First, technicians in Bremerhaven screw a so-called rotor blade clamp onto an approximately 40-meter-long rotor blade. They also provide the component with sensors designed to monitor the forces working on the blade during the test. The cables are taped to the plate surface. Now it's ready for the rotor blade testing station. Hydraulic cylinders are attached to the rotor blade clamp in a hall some 80 meters long and 20 meters high. "72 thread bolts provide a solid hold on the 6-ton rotor blade. The bolts are anchored to a 700-ton mounting block. The engineers tighten the nuts with a hydraulic wrench.
In this test, we oscillate the blades in both directions at the same time using an eigenfrequency to simulate what loads the offshore units can endure during 20 years in operation.
While the final rotations are carried out by hand, engineer Falco Böckner inspects the 40-meter rotor blade.
Hi, Stefan. Everything looks good here. Let's start the test.
Before giant rotor blades like these can be mounted on a wind turbine, they have to undergo fatigue tests that demonstrate they've been constructed using the latest technology. The hydraulic cylinders pull on the blade with a force of nearly 1 ton. The testing hall in Bremerhaven is one of the world's only facilities where the blade is loaded simultaneously in 2 directions. Since this happens at the exact same frequency at which the blade would oscillate on its own, extreme amplitudes are reached. That way, the test facility simulates 20 years of wind loads in just under 3 months. Measurement data from more than 200 sensors are compared with theoretical data. If the data sets concur, the engineers consider the blade a flawless construction.
We've determined no mechanical changes in the blade structure. That assures us the blade can withstand extreme conditions at sea.
Autumn 2009. These Alpha Ventus rotor blades also underwent testing. A cool October day, 60 kilometers off the North Sea coast. This is where they have to withstand 20 years of rough conditions. A special jack-up barge called the Buzzard delivers the components to the offshore construction site. Time is running out. Once the autumn storms begin, offshore work is impossible.
I can't really make a prediction, because if you receive the weather forecast, the 12 hours can be completely different. You have the tide, you have the swell, you have the winds. Okay, there are limits. This is the North Sea, it's not the...
Tugboats pull the Buzzard out to sea. The barge is loaded with 2 tower components, the rotor and the nacelle of the wind power facility. A damaged load would have catastrophic consequences. The Buzzard extends her supporting legs during the voyage, allowing her to quickly anchor them on location. But the maneuver is not without risk.
As you can see on the screen, there are cables over there. I can't lower them too low, otherwise we might have a chance to drag the cables with us.
The Goliath is in sight. From this platform, a crane is to place each component on the steel foundation. But now the weather turns. The tugboats try to stabilize the Buzzard with anchor chains. To be unloaded, the buzzard has to be 2 meters away from the Goliath. Only then can the jack-up rig fully extend its supporting legs. Only the anchor chains are holding her now. If the jack-up rig rams the Goliath, it would cause heavy damage to the ships and to the cargo. After a few minutes, the danger has passed. The two vessels are standing safely next to each other. The buzzard is carrying the steel foundation upon which the wind power facility is to be built. The foundation is built differently than the tripod. Instead of 3 piles, a so-called jacket is anchored to the seabed with 4 piles. It's built like a classic steel mast made of standardized parts. That lowers costs. The long-term test is meant to show what kind of foundation is best suited for the sandy underground. The crane lifts up the first tower component. To move it around the bridge, the crane has to roll forward carefully. A difficult maneuver in the narrowest space. 100 tons are suspended just a few centimeters in front of the bridge. At 1 o'clock in the morning, the utmost concentration is demanded from the entire crew. But then it happens. The tower segment slams against the railing.
It depends on the banksman. We nicked the railing a bit with one of the tower components, but I don't have eyes in the back of my head.
Around 1 hour later, the tower segment is placed on the foundation. A little later comes the second tower component, the nacelle. And early the next morning, the rotor. On November 16, 2009, all 12 turbines are installed. And since the spring of 2010, they've all been delivering power to the network, providing electricity to more than 50,000 households. Through rain and shine, day and night. And that's not all. More than 1,200 sensors are distributed over 2 facilities. They provide information about nearly every movement or load of the rotor blades, the nacelle, the tower, and the foundation. They provide a wealth of data via undersea cables. Part of this information arrives some 300 kilometers southeast, where it's evaluated at Hanover University. There's even data on the scours and the washed-out foundation.
The natural measurement data we compiled from the alpha ventus test field reveals for the first time that scours are not only forming around the foundation piles, but as we saw in our model experiments in the wave flume, a larger scour is forming directly underneath the tripod structure.
The water current not only washes sand away from the piles, it also forms a large hole directly underneath the giant steel foundation. But the data indicates that the scours have reached their maximum depth. And there's more information as well.
We want to find the best position for all the sensors in order to ensure optimal monitoring of the wind power station and to optimize maintenance. And eventually, we'd like to give advice on how to conserve materials in order to make offshore wind energy more economical.
The scientists hope to identify the Achilles heel of the wind power facilities. That means finding out exactly where the sensors must be placed. That would create a perfect monitoring system that delivers information about when the next maintenance should take place and where material can be conserved. That would save time and money, making the technology as a whole more economical. The scientists are not only researching the optimal construction of offshore wind power plants and their integration into the North Sea ecosystem. The electricity produced by the wind power plants is also an object of scientific investigation. Just a few kilometers from the coast, not far from the East Frisian town of Norden, the undersea cable carrying wind power to land comes to an end. This is where the green energy enters the normal power grid. If winds on the North Sea are blowing faster than wind speed 5, that produces 60 megawatts. But Fraunhofer scientists like things exact. They want to know precisely when the offshore units are delivering how much electricity. But there's a catch. The network demands a constant equilibrium between power production and demand. If factories and households need more electricity, that means the power plants have to deliver more kilowatt hours. If consumption falls, they have to lower capacity at once. Otherwise, the grid collapses and there's the risk of a blackout. But there's no way to influence the production of wind energy. As a result, conventional power plants will have to adapt their capacity to the irregular supply of wind power as well as fluctuations in demand. In order to do this, power plants need exact predictions for the days ahead. And that's exactly what the Fraunhofer scientists are working on. Their goal is to provide conventional power plant operators with information on how much North Sea electricity is forecast over the next 2 days. To make these predictions, they use a very special kind of data.
We use historical wind forecasts and historical measurements of the Alpha Ventus wind farm's electrical output. We then use this historical data to create a model for predicting the Alpha Ventus wind farm's future output.
The scientists look to the past in order to predict the future. They compare historical weather forecasts for a given day with the actual amount of power delivered. These results help the scientists improve a special mathematical model. The optimized model then uses current wind forecasts to calculate future energy amounts. In the control room where the operation of Alpha Ventus is monitored, scientists are testing their latest forecasting tool. The red curve represents the capacity forecast of Alpha Ventus for the last 2 days. The technicians call up the curve for the actual power delivered in that time period, and the match is very close.
We did a pretty good job with these 48 hours. Now we just have to keep improving the model with further data.
The test shows that wind power can be planned, making network integration possible. But there's still a lot of research to do in the expanses stretching over the North Sea. Aerodynamically, the zone where wind energy is produced remains uncharted territory. We know exactly what kind of turbulence a jet experiences at 10,000 meters above the Atlantic, but no one can describe the turbulence 1 to 200 meters above the North Sea with any accuracy. And this unknown area is precisely the zone where the rotor blades are expected to operate undisturbed for 20 years. And that's not all. Currently, the individual wind turbines deliver 5 megawatts of power. In order to lower the production costs of wind power, that capacity needs to increase. In the future, 20 megawatt units could deliver 4 times that amount. But if future turbines are built with today's technology, they'd have to weigh 8 times as much. The rotor alone would weigh nearly 300 tons, equaling the mass of 8 tractor trailers rotating once around its axis every 5 seconds. The engineers want to learn more about the wind in offshore parks. Only then can they construct the optimal blades for existing conditions. And only then could they finally reduce the weight of the rotor blades. Scientists at the University of Stuttgart are putting together a model unit in a large wind tunnel. A special curtain ensures that indrawn air flows evenly into the tunnel. On the other side, a rotor with a diameter of nearly 6 meters produces underpressure. The wind engineers are looking beyond the wind that blows onto a turbine.
We're investigating the wind field behind a wind energy unit. That means looking at the turbulence that develops through the rotor to find out exactly what hits the second and third rows of wind turbines within the wind field. Once we know that, we can better predict the energy exploitation of these units, enabling us to increase their energy exploitation.
The optimal positioning of each turbine in a wind farm is a further research goal. A fog machine is used to make the air currents visible, along with the turbulence. Several 100,000 liters per second flow into the 20-meter-long tunnel. The scientists capture the results with a camera, allowing them to document the turbulent zones behind a wind turbine. To find out even more about the unknown aerodynamic zone above the high seas, and to record even more precise measurements, the scientists experiment in a laboratory using the model of a special laser scanner. Installed on Alpha Ventus, a bigger version of this device with a more powerful laser could scan the area surrounding the wind power unit. That way, scientists could determine the exact wind speeds within the offshore wind farm. But before this technology delivers useful results to the outside world, the software that controls the scanner will have to be calibrated. A more extensive light detection and ranging system known as LiDAR is flown out to a wind power unit. Working out here is risky business. It's a job for specially trained professionals. If the wind gets too strong, the maneuver is broken off immediately. It's too dangerous. The laser is safe in the nacelle. The laser is installed right behind the rotor blade. Several units shoot the laser rays into the surrounding area at the speed of light. The rays possess a very specific wavelength. The air over the North Sea is full of tiny particles called aerosols. They're too small to recognize with the naked eye. The laser rays strike these tiny particles, which then reflect the rays. That creates a physical effect. The wavelength of the reflected light is different from the laser rays. The faster the particle moves away from the laser, the longer the wavelength. If the laser measures in front, it has the exact opposite effect. The faster the particle moves toward the laser and in the direction of the turbine, the shorter the wavelength of reflected light. The reflected laser ray hits special sensors that measure the difference between the wavelengths of incoming and outgoing light. The difference is used to calculate the speed of the aerosols. And that gives an exact measurement of wind speed to the 10th of a second. The LiDAR system captures every gust of wind in front of the unit and every swirl of turbulence behind it. The measurement data is evaluated at the University of Stuttgart.
Here we have the first measurement data from our nacelle-based LiDAR measuring system. And the first results look very good. That means the measuring system we developed here is working. For the first time, we can now interpolate the entire wind field. In other words, we can use the points of measurement to interpolate the areas in between and make assertions. And these data points are highly suitable for verifying further wake models.
Special computer programs visualize various wind speeds behind the wind power plant. Green stands for low and red for high wind speeds. The stark differences behind the plant are easily recognized, and that means heavy turbulence. Thanks to this data, Stuttgart scientists are able to describe the zone behind an offshore unit aerodynamically. Ultimately, they want to give engineers recommendations on where to place the units in a turbulent wind field so that energy is optimally exploited. They not only rely on data measured in the real world, but also on a complex mathematical program that breaks up the area surrounding a wind power plant into millions of tiny cells. A high-powered computer calculates all of the wind speeds for this extremely detailed model. Scientists visualize the research results with the help of a 3D screen. The model on the right is based on real measured data. The one on the left is based on theoretical and mathematical data. Scientists control the simulations with a 3D mouse. And they directly compare the two models. Through this comparison, the theoretical and more detailed model can be further optimized, and more precise assertions can be made about real-world wind conditions. But scientists are not only interested in the zone behind the wind power plant and in optimizing the energy exploitation of the entire wind farm. The LiDAR device also analyzes the turbulences in front of the unit. And that's why scientists have placed a 70-kilogram grid in the wind tunnel at the University of Oldenburg.
Based on the LiDAR data we received from measuring real wind conditions on site, we can realistically recreate these conditions here in our wind tunnel using this active grid and the active axis.
126 flaps swirl the air flowing out of the wind tunnel. It's an attempt to recreate the turbulence captured by the LiDAR device over the North Sea. A laser is placed under the wind tunnel. A mirror directs it into the airstream, making it visible. As long as the flaps don't move, there's a completely steady airflow through the tunnel. "16 axes control the flap's rotation down to 1/100th of a degree. The individual layers of air are mixed together. The wind tunnel is now experiencing the same aerodynamic conditions found over the North Sea. Researchers in Oldenburg install a segment of a rotor blade model inside the wind tunnel. They want to make assertions about the exact forces at work on a rotor blade. Until now, these measurements were only taken in wind tunnels that produce a laminar or steady airflow. That means the experiments actually took place under unrealistic conditions. For this experiment, scientists also fastened special glass walls to both sides of the tunnel. The walls are then covered with 80 special sensors that measure air pressure. Air flows into the wind tunnel, and the grid produces the real turbulence. A variety of air pressure zones are created around the blades. The sensors measure the pressure, allowing researchers to make assertions about the exact forces working on the rotor of an offshore wind turbine.
A blade is a very complex formation. It has a variety of profiles at different distances from the hub. Based on our results, we can give engineers advice on what the dimensions of a blade should look like, so the blades are not underdimensioned or overdimensional. That way, engineers can conserve materials while making the whole thing cheaper and bigger.
Researching the unknown aerodynamic zone over the North Sea brings important information to light. As a result, engineers can optimize the rotor blades and perfectly position the individual wind turbines in an offshore farm. And the vision of especially large and powerful rotor blades at offshore farms with maximum energy exploitation could become a reality. Several offshore wind farms with a capacity of some 25 gigawatts are scheduled to appear in the German North Sea by the year 2030. The farms could provide 15% of the country's electricity needs. The facilities could be linked to other farms in the North Sea with a so-called supergrid. If the wind is strong and the offshore units produce more power than needed, the excess electricity could flow to Norway over special undersea cables. That would provide Norway with a part of its energy supply. In a country of mountains and lakes, melting water in the spring is stored in hundreds of reservoirs. Countless hydroelectric plants produce power in Norway, providing the country with 99% of its electricity needs. If excess wind power flows into Norway's network, the hydroelectric plants temporarily shut down, and electricity keeps flowing. When the wind dies down, power flows once again from the hydroelectric plants. The renewable energy held back in Norway can be sent by undersea cables to Central Europe and also to Germany, providing the country with renewable energy even when the wind stops blowing. The networking of renewable energy, the research of foundation structures, towers and rotor blades, the recognition of ecological balances, the optimizing of forecasting tools, and the investigation of aerodynamic environments. The RAVE research program at Alpha Ventus delivers important knowledge for a vision of the future. A future where large and powerful offshore wind farms soon deliver a substantial portion of the electricity that used to be provided by nuclear power plants, fundamentally changing Germany's power structure.